Yeah, so thank you, the organizers, for this great opportunity. This is a really phenomenal workshop with many very well-known experts, and it's been a pleasure to learn new things. So I'll talk about new opportunities for primordial black holes, and I just moved from UCLA as a Kavli Fellow to Kavli IPMU. And let us begin. So as previous speakers mentioned, there's not much introduction needed for PBH. They can form in the early universe, and a lot of important work, of course, done by Bernard Carr in the audience. And why PBH? Again, we already heard a lot of motivations, and we are now in the era of gravity wave astronomy. Again, a lot of important work has been done by people present in this workshop. PBH can solve astropuzzles, and important work has been done by Bernard, by Dolgov and Kachov, and so on. And so, of course, we all like PBH. And some general themes that people have been considering for future work is that typical formation models from inflationary perturbations usually require tuning. And of course, since PBH parameter space is very big, we're always looking for new exciting observables. And to make some progress on this front, on these two themes, let me start by telling you about black hole formation from scalar fragments. And this is the work in a series of studies done together with Eric Kotner, Alex Kusenko, and Misao Sasaki, and some early related ideas have been found in paper by Zeldovich. And we start with just scalar fields as high energy phenomenologists. People really like scalar fields. Of course, they're well motivated in BSM theories, especially in SUSY, where you expect hundreds of flat directions that are usually charged. And post-inflation, self-interacting scalars could fragment due to instabilities and form localized objects such as cue balls for complex fields or oscillons for real fields. And this is similar to Jeans instability in gravity. And in fact, what we have shown together with Yamazaki-san and some other people is that, in fact, if gravity is the weakest force, as motivated by some theoretical arguments for weak gravity conjecture, fragmentation is even more generic than previously thought. And the basic idea of this mechanism is that if you just look at some simulations, so you start with some condensate, you get some fragments, but because the process is stochastic, you can envision that there will be some rare regions where the overdensity is sufficient that you can collapse to PBH. And I'll skip the details because of time, but what is interesting here is that the PBHs from overdense regions and such formation are unrelated to perturbations from inflation. And so this sort of addresses the issue of tuning of the inflaton potential. Another interesting thing is that just doing some parametric numerology with some typical potential, you will see that low-scale supersymmetry naturally will give you PBH in the open parameter region. So that's, of course, nice. But of course, the total fraction is model dependent, and depending on the things you stick into your model, you can arrange PBHs all over the place. And another very interesting thing of such formation is because you form PBHs from matter-dominated era, where a lot of pieces are flying together and there's some angular momentum, you in general expect a big black hole spin. And that is interesting because in the usual scenarios, it's not so easy to arrange PBH formation with big spin. So that's an interesting feature. Now, another thing you can do with scalars is consider formation of PBH from Bubble Multiverse. And a lot of work has been done on this by Vilenkin through a series of studies, and some preliminary work has been considered 3 decades ago. And recently we revisited this again with Sasaki-san, with astrophysics experts at IPMU and people at UCLA, and recently published in PRL. And the basic idea here is that you start with a multi-field inflation, and of course this is well motivated, especially if you're considering top-down theories. For example, in string application, you have hundreds of scalars. So a lot of people like multi-field inflation. You will generally end up with a complicated potential. And as you roll down your potential, you can tunnel to some other vacua, and so you will have a bunch of bubbles forming. And the bubbles will collapse and form black holes. But in fact, some bubbles can be so big that they have a very non-trivial space-time structure inside of them and can support inflation inside the bubble. But whatever happens inside the bubble, from outside observers where we are, they all form black holes. And the interesting point for observation of these scenarios is because depending on the bubble formation time, you can get an extended mass spectrum of black holes from different sizes of bubbles. So that is very interesting, and we proposed a sample potential This is a tilted Mexican hat. This is just an example. You start here, you roll on the rim, and you tunnel to the middle. And as you tunnel, you form bubbles, and then as you tunnel past the minimum, the tunneling shuts off, but now you have a distribution of bubbles. So this is just an example. And what has been very exciting is that recently, and we already heard some talks about this, is that by IPMU-led observations with Super HSC of Andromeda Galaxy of microlensing survey, they have detected a very interesting event. And the results published in Nature Astronomy recently. And what is interesting is that this event is consistent with such a broad mass distribution from the PBHs from Bubble Multiverse that I have been advertising, where you can explain all of dark matter lying in the open parameter space. And so this is, of course, very exciting. And in fact, you can go one step further and generalize this model in such a way that you can construct an even more general spectrum that allows you to hit simultaneously a bunch of observations that people usually address separately, such as the dark matter, the HSC event, the LIGO events, and supermassive black holes. That is, of course, is very nice. And I'm happy to report that right now we have, together with astronomers at IPMU, we have secured observation time on HSC, and observations are happening right now to test this scenario further. And so this is very nice. And so, so far I have presented basically two different scenarios from scalars where you can get, for example, high spin, but a more peaked spectrum or a broad spectrum. So these are different interesting possibilities. Now going more into the observational aspect, so I will now discuss about PBHs making gold, and this is work with Alex Pusenko and George Fuller from somewhat from a year ago, basically from 2 years ago. And as you know, with the observation of neutron star merger, a lot of people have thought, well, now we have the explanation of the heavy element production because of the R process nucleosynthesis from the merger. But is that so? Has the fate of the origin of heavy elements have been decided? And maybe not so quickly, because the recent reanalysis shows that, in fact, the merger contributions have been very overestimated. So there have been actually a bunch of recent news releases by popular sources saying things like, oh, something is radiating golden universe, but no one knows what is it. So the puzzle remains. And what I would like to advocate is that asteroid mass primordial black holes that make up dark matter can help us with this puzzle. If small PBHs are captured by neutron stars, they can consume and explode the neutron stars, and you will get a bunch of Newton-rich material flying out that can contribute to our process nucleosynthesis. And in fact, you can explain the abundance in Milky Ways and ultra-faint dwarfs of heavy elements for some parameter space. So that is, of course, is nice. But in fact, as shown again in this work, but also in some separate work that I have done independently, is that PBHs interacting with compact stars are not just good for considerations of our process, but they're interesting as compact as laboratories in general. And you can get a bunch of interesting observables. And one of them is explaining explaining positron production relevant 5-length KV galactic center axis. And as we separately showed, you can also do this just from regular SNS. You can get a bunch of interesting new signals, such as orphan kilonova without the gravity waves. So in usual mergers, you get a kilonova, but you have a merger gravity wave accompanying here. You can also get FRBs. You can get solar mass black holes, which I'll discuss next. If a Greenwich index forms, you can get a GRB, also without gravity waves. So that's a new type of signal. And you can also get solar mass microquasars, which is also a new type of astrophysical signal. So that is, of course, very nice. And so compact stars interacting with black holes are very interesting for many different directions. And there's more work to be done. Now, going to the solar mass black holes, what is the origin of such black holes? Now, since solar mass black holes are not expected in standard astrophysics because of the Tolman-Oppenheimer-Volkoff stability limit for neutron stars, you do not expect anything below, let's say, 2.5 solar masses. A lot of people think that this would be a definitive signature of PBH, or you can also have a bunch of particle dark matter being captured from black hole and collapse and also produce a solar black hole like this. Now, what is the relevance of this is that because very recently this year, LIGO detected events consistent with 1.5 to 2.6, let's say, solar mass black holes. And LIGO by themselves, they cannot discern, is that a black hole or a neutron or a heavy neutron star? And so this is very interesting. And the obvious question is, okay, so suppose you now have these candidate events, what do you do with them? How do you distinguish the origin of such black holes if they are there? So, but there's a very simple, powerful test that we proposed 2 months ago, basically, with Alex Husenko and George Fuller, is to use the solar mass black function. Because even though you can form primordial black holes of solar mass, black holes of solar mass that are formed by destruction by small PBHs or by particle dark matter accumulation of neutron stars, they should follow the mass distribution of neutron stars. And that is, of course, is totally different than solar mass black holes, primordial black holes formed in the early universe. Because neutron stars do not have just a single peak distribution, but actually they have some spectrum. So what you can do, you can take your candidate event black holes and compare with the neutron star mass spectrum. And just even with stellar events, you can already make some very interesting conclusions, such that large candidates are probably not coming from either small PBHs or particle dark matter interacting with neutron stars. And I would also like to point out some interesting related ideas, this also by some of the organizers of this workshop, and the paper came out right after our paper. So please also take a look at this. And now let me also mention, what about intermediate mass black holes? So these are the heavier ones. And LIGO recently detected a 150 solar mass merger mass event. And this is claimed as the first definitive intermediate mass black hole observation. And what we have proposed in this work from the summer is a general new cosmology independent observable to test such black holes, namely use gas heating. And the idea here is very simple. As a black hole is traversing the interstellar medium and the gas around it, it can interact with gas through various mechanisms such as dynamical friction, which is basically gravity drag, accretion disk photon emission, so there'll be some photons being emitted, and also outflows winds, which basically means protons emitted. So all these things, they deposit energy, and then you can ask an obvious question, well, how much did my interstellar medium gas got heated? And so you can go to a very nice system, which has nice properties, such as dark matter-rich Leo T dwarf galaxy. And turns out that you can put a very impressive limit over a large parameter space that is independent of cosmology. And here's the LIGO range. And so that, of course, is very nice. And I would also like to mention that, in fact, you can use the same idea. And after our proposal, there was a paper by Kim that pointed out that you can also do evaporating black holes and constrain them with heating. And we later studied and corrected this effect, and also studied the effects for spinning black holes in the paper with Ranjan Lach and Philip Lu very recently. But there's more work to do with PBH gas heating. So, but this is a new idea. And so let me now summarize. I know I sort of sketched a bunch of things, but this is now, I think, a really, truly renaissance era in PBH research, because mainly of the intimate synergy with multi-messenger astronomy. There's the two mechanisms I presented from scalars. They basically illustrate that you can get some very interesting effects, such as high spin or broad mass distribution. And of course, it's very nice that you can test some of the things in very upcoming times. Also, there's many still unexplored observables, of course, over the vast parameter space. Some of them are associated with compact star interactions. There's a simple, powerful test you can do for solar mass black holes, namely just use the black hole mass function and look at statistics. And there's a new cosmology-independent way to look for black holes in general, either evaporating or the bigger ones by gas heating. And I hope with all of this, we're marching towards definitive answers regarding the role of PBH in physics and dark matter. And thank you very much.
Thank you. Right on time. Do we have any questions from the audience for our last speaker? Nor from the YouTube channel. There are lots of information, I guess, but I do have myself then one quick question about the last point that you're making and this new general cosmology independent probe of intermassive black holes. We do have a question, so I'm still going to ask mine quickly. I just wanted to know whether this type of bond, there is a literature about constraints from primordial black holes coming from the accretion effects in the early universe and so on. Is that a completely new probe that you're mentioning, or is it similar to those ideas but applied to a different type of system? What is the...
Yeah, so thank you for a question. Yeah, sorry, I've been a bit too quick because of time. I just wanted to sketch different ideas. Right, so this is a different totally probe. So a lot of constraints on CMB, and in fact, a lot of them are done by some of the members of the workshop. There are constraints, but they are at a different time scales. They're not constraints on gas heating. So gas heating is a totally new constraint and has not been considered previously for PBH in any context. So,
Okay.
although I do want to mention there has been some work, especially by Bernard Carr, that studied, Bernard, of course, can discuss this more, but they studied some effects on stars, as far as I remember correctly. As a black hole passes, what will be some dynamical effects of stars? So there's some energy transmission there. So that would be somewhat related, I guess.
Okay, so I'm going to take one question from the audience and then we're going to stop. I'm going to take the first question that comes by Patrick Dasgupta. Concerning FRBs, does your model naturally explain why emission dominates in the radio?
Yeah, so for the FRBs, so this is one of the many different signatures that I mentioned of small PBH interacting with with neutron stars. And the basic idea here for FRBs is that a neutron star is a highly magnetized object, and the magnetic field is usually stored in, so to speak, flux tubes, and they're quite rigid. But as small black hole inside the star eats the star, the magnetic field energy must go somewhere that's stored in the flux tubes, right? And it was shown by some other people that, in fact, during such a violent event, it is very likely that a percent level will go into radio. And that is a natural source for a non-repeating FRB.
Okay, thank you very much. So we do have an extra question from the audience. I don't know if we have time to take that. I'm going to say let's take it, since now we will have a lunch break and maybe you have a quick answer. So can you say something about the recent nanograph results and your thought on whether PBH could explain that?
Yes. So actually, we had a paper, I did not mention it, but we had a paper on nanograph that, in fact, this is a very interesting shape right here from such bubble multiverse PBHs is able to address the nanograph access. And also some additional work on a similar type of study has been done by Antonio Riotto, so please also look at his paper. But the interesting point here again is that we are now getting observations from HSC that will test this whole possibility. So they will probe down here. So that's very exciting. So, but yes, there could be relation to nanograph, yes.
All right, thank you very much for being on time. Let's thank all the speakers again for fantastic talks.